Hello, viewers, and welcome to my homework 2C. My microphone won't get in front of my mouth. That's cute. I am going to implement Broyden's method with step size adjustment and inversion of the Jacobian as necessary when progress is slow. So what does that mean? Well, basically, I'm going to implement Broyden's method, which is a method for finding the roots of functions similar to secant and Newton. In fact, it's basically Newton's method with a little twist. And then I'm going to use that to calculate then I'm going to use that to calculate the roots of a function. And I'm going to need to make a few exceptions to Broyden's method in order to get it to work correctly. But when all is said and done, it should be pretty interesting. So, let's look at this. This is Broyden's method's Wikipedia page. So, in numerical analysis, Broyden's method is a quasi-Newtonian method for finding roots in k variables. It was originally described by C.G. Broyden. So, what this is going to go on to tell you is that you're basically going to take Newton's method, and you are going to solve Newton's method using a Jacobian for every iteration. So what does that mean? Well, if we go back and look at what I did for, and I left my code for Broyden's method in there. I will delete that in a second. But if you look at what we did for Newton's method, we took the Jacobian, or we took the inverse of the Jacobian every single time I wanted to iterate through Newton's method. Now, this is challenging in computers because the inverse of a matrix is pretty hard to calculate. So what we're doing right here, this Jack's NumPy lineage inverse, that's kind of hard to do. That takes a lot of computing power. So what's powerful about Broyden's method is that it lets us approximate the inverse of the Jacobian. So how do I do that? Well, so consider in nonlinear equations consider a system of k nonlinear equations. So this is a matrix of, with these sort of dimensions right here. You can take the Jacobian of the matrix, right, and you will end up finding that the Jacobian of the matrix, or I guess you could say, basically we're going to approximate Newton's, or this is Newton's method, right? Our next guess is going to be our first guess minus the inverse Jacobian times f evaluated at that first guess. So that's what we did in Newton's method. But then you come down here and Newton says, well, this is inverse Jacobian is really hard to calculate. I have a way to calculate it. He uses the Sherman-Morrison formula to update directly the inverse of the Jacobian matrix. So he says that the inverse Jacobian at a certain guess is just your last guess's inverse Jacobian plus this big long thing right here. And there's like a pretty complex derivation that I'll get to in the next video to kind of prove this is true. But for now, let's just go ahead and maybe try to program this out. So I am going to, just in summary real quick, I'm going to take Broyden's method. I am going to start out with a guess for the inverse of the Jacobian. There's a lot of things you have to do to kind of make an exception for this. But eventually I'm going to go through and continuously reevaluate the inverse Jacobian and keep estimating the inverse Jacobian while I'm continuing to try to get a better estimate for the independent variable. And once again, this is all to solve for the roots. And you can see there's an iterative process, and eventually it gets me what I'm looking for, which is the same initial guesses as I started out with. So let me delete these two pieces of code, and then I will restart and run all. So just restart the runtime so I'm not getting it messed up with any variables I used in the past or anything like that. And let's try to maybe do Broyden's method for this function I used in the last episode, just fun function. So I'm going to start out with Newton's method, actually, because I think that's just the best way to go about it. Or with the Newton's method I programmed out last time, because I think I'll be able to draw some comparisons. So instead of defining Newton, let me go ahead and define Broyden. And what do I want to do with Broyden's method? Well, for Broyden's method, I want to take in a function I'm going to take in some initial guesses and then go through a certain number of iterations and solve so that the value of the function is less than a certain tolerance. It's basically so the value of the function is 0. So I'm going to start out with the Jacobian is going to, well, for Newton's method, I started out by defining the Jacobian using Jax's automatic differentiation. I can't do that in Broyden's method because that's kind of hard to do. And then also, I can't do this down here, taking the inverse of the Jacobian in Broyden's method. So how do I work my way around this? Well, let's take a look. It appears as if I need to make an estimate for the Jacobian. So if I go ahead and drag this over here, and drag this over here, then I can maybe just start out and, well, I need an estimate for the Jacobian. So I need some initial guess for what the Jacobian is going to be. What I'm going to do is I'm going to go to NumPy, and I'm going to use the identity matrix, which is abbreviated as EYE for some reason. And I'm just going to say it's an identity matrix of size, whatever size the initial guesses have. Now this is of course not going to be anything like what the actual Jacobian of f is, but who cares? So then I can go ahead and take the inverse of the Jacobian, and my initial guess for the inverse, maybe I'll just say that that is the initial Jacobian. Once again, super not correct. The inverse is not going to be the same thing as the Jacobian, but let's just leave it that way for simplicity. And I'm going to go back and modify this later. So I would just say that my next guess is going to be my first guess minus this inverse of the Jacobian of f, matrix multiplied by f evaluated at the initial conditions. So then I have this new guess. I can come in here. f1 is just f evaluated at x1. If the magnitude of f1 is less than the tolerance, break out of here. But if it's not, go ahead and redefine these things. And in Newton's method, I would just rerun the equation. But in Broyden's method, I need to get a new estimate for the inverse of the Jacobian. So how am I going to do that? Well, this is what the Sherwin-Morrison formula tells me how to do. I can take my last guess. So this is the current value of the Jacobian inverse. And then I can add a certain value, or I can add the value of this function. And it's a pretty long, drawn-out function. So that's going to be, well, okay, I need to backtrack for a second. The Jacobian is just going to be delta x minus, what is this delta xn? Well, delta xn, if we look up here, is just the current guess minus the initial guess. And these are both arrays of those two guesses. So I can come up here, and before I think I define x0 and x1, I need to define dx, and I need to define dx as x1 minus x0. And then I need to define df as f1 minus f0, right? So I need to generate these dx and df terms. So now that I've done that, this delta, or I should say delta, really, but I'm just calling it d within my code just for simplicity. But yeah, so now that I've done that, I'll put a space in there just to make it a little bit more clear. Let's go ahead and try to program this out. So the change in x minus the inverse Jacobian, or the, I missed that there, minus the inverse Jacobian, matrix multiplied by the delta f, so the change in f, so that's df. And then this whole thing needs to actually be matrix multiplied by the transpose of the change in x. So to get a transpose in Python, you just put a .t at the end. And that is matrix multiplied by the inverse Jacobian. And I'm going to put this whole top term in parentheses, just for clarification. I don't think it's really that big of a deal. And then I want to divide this top term by this bottom term down here, which I'll maybe just call that the denominator. Actually, yeah, just to make it fit on the screen better, I'll call that the denominator, DEM, not election related. And then I will code out this denominator. So the denominator is just going to be the change in x, or the transpose of the change in x, matrix multiplied by the inverse Jacobian, matrix multiplied by delta f by d capital F. So sweet. So this is a recalculation of the inverse Jacobian. So with that, Broyden's method should, in theory, be ready to go. Like, I programmed it all out. Let's go ahead and run this code. I don't get any errors, so let's maybe try to do a prediction of Broyden's method. So I will say that f, or my function, so capital F is just going to be lowercase function, and then my initial guess, which I also need to specify, will just be whatever my initial guess was up here. It looks like it's a Jack's array of 0 and 0. So that's pretty sweet. Let's see what happens. It's going to run, and I'm going to get a device array that is infinity by infinity. So it's telling me that basically something is screwed up here. So maybe let me go through and let's create a print at the very end of the function. And I want to be printing out, for every iteration of this for loop, I want to print, what do I want to print? Well, I'll print whatever iteration we're on, so that's I plus 1. Then I will also print, I'll print x1. I think that's a good thing to show. And I think for now, that's all I'll just print f1 for now, just to sort of show. And, I'll print f0 and x0. It shouldn't be a huge deal, but I think that's just better. So, yeah, let's see what happens. Well, it runs 100 iterations. That's going to get annoying to run through every time. So maybe let me switch that to 50 if I'm thinking about it. And so it starts out with our initial guesses, and it calculates that the value of the two functions that we're appraising are 0.5 and negative 0.5 at these two values. So then it goes through and sort of tries to re-guess, and it keeps doing some other stuff. It kind of gets stuck in a loop for a minute until it eventually gets close to 0, and then, I don't know, it looks like things eventually spiral out of control, and you start to see the values of, or each guess of x0 is somehow getting further away from, each new independent variable is resulting in a function value that's greater. So it's getting further away from 0. So this is a problem. It's causing almost like a runaway reaction, right? And we're getting these really high numbers, and then NaN means it's kind of like it's gotten to infinity. It's too high for it to even calculate. So this is bad. This is not what we want to be happening, of course. So how can I go about fixing it? Well, let's maybe start a new loop. And what I want to do in this loop is I want to go through and I want to say that, I want to go through and I want to check and see, am I getting closer or farther from 0? So what I can maybe do is I could say that if the magnitude of function 1, or of my guess of function, is greater than the magnitude of my original function, whatever I started this iteration on, then if that happens, I want to change what I'm doing and maybe do a partial step. And that's what C is asking me to do a step size adjustment. So how can I do that? Well, let me redefine how I make a step. So right here is sort of when I make a step in the function, right? I'm saying that x1 is just going to be x0 minus is inverse Jacobian matrix multiplied by the function evaluated at my guess. So maybe let me go ahead and I will define a new variable. I will say, So I already defined this down here. I said dx is x1 minus x0. Well, let me go ahead and define this as dx in this function, and then I'll get rid of this x0, and so this is like dx equals x1 minus x0, which is just this up here. Now I can say that x1, so my next guess of x, is just going to be x0 plus dx. So this is pretty sweet. It doesn't necessarily help us out so far, but what if I don't like the way I did this and I want to modify it, and so dx is kind of the step we've taken now. Well, if I want to modify the step, I could maybe say, I'll define just some variables alpha, and I'll say that alpha equals 1 by default. So now what I do is in this while loop, I will go ahead and say, oh, well, I took too big of a step. Let me take a smaller step. And that smaller step is just going to be whatever I just did times alpha. Now, of course, my alpha value is 1, so this right here is the same thing as what I've already done. So before I do that, let me come in here, and I will say that my alpha is going to be equal to 0.75 times whatever alpha was before. So this alpha value is going to shrink, and I'm going to be able to reappraise or take like an incrementally smaller step each time. So this is pretty cool. This now allows me to say, oh, well, if I step too far and now f is growing too fast, well, now I can take a smaller step and see if that works. So let's go ahead and maybe run, well, I shouldn't run this yet, because now instead of reporting the value of f0, let me go ahead and maybe try reporting the value of alpha and see, every time, what value of alpha do I get to as I'm trying to run this formula. So now if I run this function, I can run Broyden's again, and let's see what happens. It's calculating. It's doing a lot of work. If this gets past 20 seconds, I might go ahead and cut it off, because I probably did something incorrectly. Let's see. It doesn't like all of this. Yeah, it's kind of getting stuck in an infinite loop, and it looks like it's doing this after stage 6. So let me just stop this real quick, because something's not working out here. And let's go back and think about this for a second. So I'm saying if f1, or if the magnitude of f1 is greater than the magnitude of my first guess, so that is what I want, I think. I'm multiplying alpha by 0.75, then I am adding x1. Oh, I need to reappraise what f1 is. So f1, there's no way for it to break out of this while loop. So I need to say that f1 is f evaluated at x1. So now it should work, now that I've recalculated x1. Yeah, sweet. So I'm still getting to infinity, but it's taking me longer. And you see the last value in this list per every iteration is the value of alpha that it ended on. So the first few iterations, it takes alpha down to 0.75 and takes little smaller steps. But then, once I get past that, it eventually takes like really, really small steps until eventually I'm close to the desired value. Like these are the values of the independent variables. So I'm getting close. You can see this is similar to what I've got highlighted up here, what I got using Newton's method. But the issue is that it appears as if I'm sort of overshooting it. And I start overshooting it specifically once my value of alpha gets really, really, really small. So this is where I'm going to come in and I am going to say, well, the step size adjustment isn't cutting it. My steps are just getting so small to where the whole thing's just sort of breaking down. I need to actually do the inversion of the Jacobian just one time, just one or two times throughout the whole thing to get back on track. I think that's really what's going to make a difference here. So, the whole point of doing Broyden's method is so that you don't have to do the inverse of a Jacobian, which isn't great, but, this is kind of the best way to do it. So how can I go about defining my function so that I am using the inverse of the Jacobian, but just a little bit? Well, obviously, I'm going to want to do something here around alpha. I'm probably going to want to say something to the effect of if alpha is less than, say, 1 times 10 to the negative 10th. So if alpha is really small, then I need to make a change to what I'm doing. But before I even go about doing that, I should probably import the Jacobian as a function. So one of the things I need to bring in is the Jacobian of f. So I'll maybe just say that one of the things I need to import is f underscore jack. So this is capitalized right now, so that's not great. But yeah, I'll go ahead and get rid of this f jack I was already using and just start straight off with the inverse. And so why don't I go ahead, and since I'm importing the Jack's Jacobian of a function, why don't I go ahead and maybe just start out by doing the linear algebra inverse of that f Jacobian. And then, of course, I need to evaluate that at my initial guess. So what I'm doing up here is I'm going to run, similar to what I did before, I'm going to import the Jacobian. So I'm going to say that fjac, I'll bring it down here just to be a little bit more clear. So the f Jacobian is just going to be Jack's Jacobian of function. So in fact, I'll go ahead and call this one function Jack. And then I will just say that f underscore Jack is equal to this function Jacobian that I use Jack's automatic differentiation to get to. So now I'm going to start out with the actually calculated inverse, just to get a good starting point on my function. But then after that, I'm going to default to just using the approximations of the inverse that I'm doing down here. So that's sort of what I'm going to go about doing. Now going back here to this if statement, if alpha is really, really small and I'm not making any progress, what should I do? Well, I think what I should do is probably take in this f Jacobian and use that in order to calculate dx rather than doing it another way. So, or rather than doing it like I did up here. So I'll go ahead and copy this down here. And I'll say that instead of using this f, or actually even before I define this f-jack inverse, I will redefine f-jack inverse as the numpy linear algebra inverse of this f Jacobian, so the Jacobian of f, which I calculate outside the function and import into the function, evaluated at whatever my x0 is at that time. So it's not necessarily the initial guess I imported, it's whatever I've iterated through in the initial guess. It's whatever was defined as the initial guess, right? Not here. Right here. There it is. So now, if I do that, I've redefined dx. I believe there's something else I might need to do, right? I don't know. Let's go ahead and run this, and let's see what happens when I go ahead and run it down here. We'll see. Okay, sweet. I think this worked, actually. So I started out with my initial guesses, it iterated through, and I found that according to Broyden's method, with the step size adjustment and the inversion of the Jacobian, I found that the two values of the two independent variables, x1 and x2, are going to be 0.844 and 0.5188, and then some change after that. So if I come back up here and look, oh, that looks to be exactly what Newton's method calculated in the last video. So that's pretty sweet. Now, of course, the question is, I'm taking the inverse of the Jacobian, so am I really saving anything? Well, that's a great question. So let me go ahead and I'll define a new variable. I'll call this Jack's count. And this Jack's count is going to be set equal to 1 when I do my first Jack's inverse. Actually, I'll say, yeah, let me call this inverse count. So then this inverse count, I'm going to come down here, and every time alpha is too small and I have to do the inverse, let me count up the inverse. So that inverse count is just going to equal itself plus 1. So now if I run Broyden's method, and actually I should probably return inverse count at the end, so I need to do that as well. But now if I run it, and let's see what I get at the end. So now at the end you see I'm returning the value 2. So that means that I only use the inverse, or the linear algebra inverse, twice calculating doing this Broyden's method, whereas up here when I was doing Newton's method, I had to use it, I don't know, as many times as I iterated through. So that would be, I don't know exactly how many times Newton's method was iterating up here, but probably like 30 times or something like that. So this is computationally a lot less intense, which is super important when you're working with large functions. So this was sort of me practically implementing Broyden's method and using a step size adjustment, that's the alpha part, and then the inversion of the Jacobian, which I just did, as necessary when progress is slow. So this pretty much wraps up video C for me, or part 2C. Thank you very much for watching, and I hope you enjoy it. I will see you in the next and final part. Bye-bye.